Perfect. Okay, well, thank you. Thank you very much. So I will mention lazy learning, but it will be just a little bit of, okay, good. So yes, summary statistics link changing neural representations to behavior. Now that's a mouthful, but so the real thing I'm trying to answer here is, what is it that we should be measuring in the brain? So the problem is the following, right? I mean, experience is reshaping neural activity. Through learning, we're creating new representations of the world. And on the experimental side, we have now recent methods that can track thousands of neurons across days, weeks, months, even in freely behaving animals. This is just like some famous figure from the NeuroPixels work from Steinmetz et al. From Science, and showing basically that they could record neurons up to 300 days from cortex, hippocampus, and so on and so forth. Now, the challenge is, what do we do with this data? And in particular, we must identify, what features of this high-dimensional data actually matter for understanding learning, right? And when we're looking at these data sets, we are sort of inherently doing this. We take the data and do some analysis with it. And primarily, there's a lot of representation analysis that we do. For example, this morning, Suyun gave a very beautiful summary and talk about the manifold ways of looking into this data. But I would say that it still remains unclear whether these measurements are sufficient to explain how those changes drive behavior. I mean, I'll be talking mainly about, this came up in the morning again. This is another way of looking at data. This is representational similarity analysis. For example, here the authors were trying, we're trying to make comparisons between representations in the monkey IT cortex and human IT cortex, and we'll talk more about this, but this is just one way of representing the data. Okay, so this is the current cap. Okay, so then what I want to do today is basically come up with a proposal. So the proposal is basically what we should be measuring is measuring summary statistics of learning. Now, the contents of this talk is recently appeared as a perspective article which we published it's on archive now with my students or previous students, Jacob Zavatone and Blake Bordelon, and I thank them also for their contributions here. Okay, so what do I mean by summary statistics of learning? Okay, what is a summary statistic? So here is our sort of suggestion. We posit that summary statistics of learning must satisfy the following minimal desiderata. So we are requiring these two things. Okay, well, there will be two things from them. One, they should be low dimensional. Obviously, we don't want to report, all the data that we have. We want to report a subset of sort of smaller number of quantities from data. That's the idea of low dimensionality. And we all inherently do this whenever we're looking at data, presenting data. We always, present some statistics of it. But that's not enough. And I also say that they must be sufficient. Sufficient to what? Sufficient to predict behavior across learning. And that sufficiency comes with two sort of conditions. One, the quantities, the statistics that we have, sort of should satisfy a closed set of equations. By closed, I mean, I can calculate them through all of them. I don't need any extra information. And then, of course, these sufficient statistics should also predict the network's performance, right? So that's what we are sort of interested in. So basically, this is a sufficiency condition. Now, when I say it this way, of course, physicists among you immediately realize that there's similar objects in physics that go by the name order parameters and that serve a similar function, although probably not introduced this way. And then I'm using the word summary statistics because this term actually was introduced by Gérard Benarous, a famous probabilist, in some papers trying to address some questions about machine learning in high dimensions, and I think it captures the idea better. Okay, so these are the two desiderata that I think that basically the things that we are trying to measure should satisfy. Now, if you have any objections and thoughts, now is a good time to object or comment. Yeah, please. Yeah, okay, sufficiency seems fine. Okay, excellent point. Yeah, Maha. So I can see the light, present light.
We have in physics, we have many situations, for example, the Boltzmann equation, and we're trying to derive an effective theory from the Boltzmann equation, which might lead to, for example, Navier-Stokes. We don't have closure, and yet we are able to make progress because we just stop at second or third order statistics and we go forward.
I mean, okay, sure. I mean, let me give examples. That's what I'll try to do and maybe illustrate what I'm going to say. Okay, yeah, I mean, you have a point. I mean, here I'm trying to say, maybe just broadly speaking, close meaning they just close on themselves. By knowing these quantities, I can calculate everything about them. That's all I mean, and propagate them in time, perhaps. But the point I want to make, okay, so maybe let me ask my questions. So the question is, of course, how do you obtain such summary statistics for the brain, right? I mean, do we know what would they look like? Is there even hope for measuring them accurately? And you can keep asking questions more and more and more about them. And I don't know the answer, right? So we're not there yet. We don't have these things. I think it's one of those things, once you see them, you will know exactly what they should be looking like. But what I can offer you today is basically where are we, right? And that means I'll discuss some examples of summary statistics from theories of learning in neural networks. And as I mentioned, the link to physics and through this order parameters, they appear a lot in, like, you know, a certain way of approaching these kinds of systems, which I call dynamical mean field theory. I'll just try to give a bunch of examples. What does closure look like? You know, and then what do these things look like? And then basically, what we do need to measure to be able to get this kind of an understanding of a system. Okay, so with that, let's just start with the simplest thing I can think of. So this will be basically just a single perceptron. What I mean by this is basically this kind of a machine. In goes an input x and out comes f of x, which that functional relationship is given by w dot x, and there's some nonlinearity over there. So we want to analyze this in a learning setting, which means, so for this, I'll use a supervised learning as an example. Okay, so I should also mention something. So let's say the dimensionality of this input x is d, and we'll think about like d being large, and then we'll think about basically an online learning setting. What that means is we're going to be given an input, a target output y mu is the sample index here, and some update rule. This update rule here is basically a gradient descent on a square loss. And then online in the sense that, you know, you see an input, you do an update, you see another input, you do an update, and so on and so forth. Now the dynamics here is, I mean, is of a high dimensional vector W, right? So it's a lot of things, okay? So, I mean, to be able to capture this system, it sounds like you have to do a lot of measurements. Now, this problem was studied by authors Biel and Schwarze, I guess that's what I say, is in 1995. 1995 is not at the frontier, it sounds like, because the meeting about frontiers. But I mean, 1995 was also a big year for this theory. And I'll give you another example of what happened then. Okay, so what they said was basically, okay, so let's just simplify the problem a little bit. Let's assume that these x's and y's are coming from a particular data model, so or which we could also call a teacher. So x is going to be just some high-dimensional Gaussian, and then isotropic Gaussian, and y, there's going to be a y that's generated by another neuron, but it will have its own weight vector w star, which will sort of be the correct w star. And what you can show is that in the limit that d goes to infinity, and there's another condition on the learning rate, you have to scale it the correct way, there appears two summary statistics here, okay? So one is Q, so this is basically the overlap of W with itself, just the magnitude of W. And the second one, R, is the W dot W star, so it's basically telling me how much aligned is the neuron's current weight is to the true weights itself. And this is, I call it a summary statistic because it satisfies my desiderata in the following sense. So, I mean, first of all, it's low dimensional, right? We are just two scalars as opposed to infinite dimensional vector set. So I'm not sure why the graphics are like this, but apologize for this. And then the sufficiency conditions are satisfied as follows. I mean, so we can show that in this limit, The dynamics of Q and R close on itself, meaning if you knew them, you can just propagate over time through this integrating this ODE, right? So you don't have to know anything else. And also, these are relevant in the sense that if you knew what Q and R was, you can exactly calculate what the test error of this model was. And so that's basically shown here. So I'm not giving you the exact functional relationships of what this epsilon is and F is, but there does exist something. Okay? So I hope this clears what I mean by being closed and also being predictive of performance. Okay, so the summary statistics are here, but these two quantities are basically explaining everything about that you want to know about the system. You know, they even have this famous figure. They were basically doing experiments. These are the circles and so on and so forth, and they were plotting these solutions of these dynamical systems. That's the solid lines, and they were showing a full match. The point again being just two summary statistics capturing all the relevant information about infinite dimensional learning dynamics. So this is one example. This particular example is basically sort of can be generalized to a two-layer neural network. Basically, the setting will be the following. You'll introduce a hidden layer. The hidden layer will have n units in them. And now, there are many authors that studied this, most famously being Sada and Soya. The paper being most famous, not the authors, but in the sense that in this particular setting here is, you keep n a finite dimensional, d goes to infinity, and then you have also a teacher model, given by here. So basically, which depends on k dimensions. So there should be dot x's here, so that's missing as well. And then you can show that there's some statistics which are given by these quantities. So these are, again, dot products of WIs by themselves and dot products of WIs by these WKs, the teacher ones. In total, if you count, basically the original system was n plus dn dimensional, right? D going to infinity, but it gets reduced to this n plus n squared plus nk dimensions. And it's a significant dimensionality reduction if the dimensions is much bigger than n plus k. Okay, so let's just stop here for a second and then look at these ordered parameters and think about them. If we were to take these summary statistics as potential descriptors of what happens in the brain, what do we need to measure, right? So first, we need to measure these W stars. So these are basically modeling data, right? So in a sense, we need to find good models of data as teacher weights. So that's a modeling question. But also, it looks like we need to measure connection strengths in the brain, right? So basically, W's are connection strengths, and that's what we need to measure to be able to fully characterize this system in the way we want. Now, this, of course, a lot of our analysis, so this is obviously a problem because, especially if you want to track this in time, if you get connectome, you can't get it in the next instant, that doesn't work. So if you were to rely on representational analyses, there seems to be a problem here. Now, we are lucky in this particular case that there are ways of estimating this R and Q through basically just correlations in activity, which would, again, if you were to take this seriously, would take some, correlations between pre-activations or voltage, let's say, or currents in the somatic currents of neurons, and then are driven by many different over ensembles of inputs and so on and so forth. So there's a path forward if you want to take this. Okay, but these kinds of summary statistics are great, but they come with these problems. We can ask also, are there other types of summary statistics? So I also want to talk about other ones, especially some of them that appear through my recent work, which I think relate more to representational analyses. And these are basically introduced in this series of work. There's just 4 papers here, and I'm going to discuss basically the first 2 of them. And just to give you a little background, the motivation for us to do this work wasn't the motivation that I'm giving here, but it was more about studying this scaling behavior of language models, the observation that as you keep increasing the number of parameters or the data set size or the compute that you throw at an LLM, the performance gets better and better and better. And in particular, this particular one, what happens if you just keep increasing parameters to infinity, meaning, what are the limits of this kind of scaling? That led us to study so-called infinitely sized neural networks and try to understand what was happening behind those networks. And then, So that was the original motivation. And I'll try to introduce, again, so we did this for a variety of architectures, including MLPs, CNNs, attention architectures, and ResNets, and so on and so forth. But I want to focus today mostly on MLPs because that's what's more relevant to what I want to say. So in this kind of work, basically, we will solve two problems. One, we don't have to come up with a model of data. So we will work with data as is, X and Y. Okay. So this is just given. It might be MNIST, whatever, I don't know, C5 times something. And for what I'm going to present, I'll just focus on training with gradient flow. It's basically gradient descent, but in continuous time. Okay, so I'll start here. So this is where the lazy learning comes into play. How you initialize the network gives you different limiting behavior. So we don't really have to understand these in details, but the idea is basically when you're initializing these networks, you choose a bunch of random numbers and divide them by a factor of width. And depending on what that factor is in the last layer, you might end up in a so-called lazy regime. Lazy here is called by neural tangent behavior, which means that the internal representations of this network is not changing. That's obviously not the limit we want. We want a so-called feature learning regime, which is in this slides are called mean field scaling. And what that means is basically you want to divide this last layer by n. Gamma 0 here corresponds to a hyperparameter that we can tune to introduce more or less representation learning, and we'll play with that again. Okay, so in this, and also another aspect of this is now a multi-layer neural network. The other kinds of order parameters were limited to studying two-layer neural networks. Here we'll be able to go deeper. Okay, so just to illustrate to you that there are differences. So this is a simulation, okay? So this is test loss versus epochs of depth 12 ResNet on C510 and SGD training and so on and so forth. So this is basically a network with a certain width. If you take this network and scale it up using one of these prescriptions, the lazy way, this is what happens. If you make it wider and wider and wider, the behavior gets worse and worse and worse. And if you scale it up using the feature learning or the mean field way, which is the good one, right, the behavior gets better and better and better, and also gets basically converges to a sort of close to a limiting behavior. It's this limiting behavior that we're going to study. You might be observing that some of these curves are looking very close to each other. Even these little kinks are being repeated across different. This is happening because we're presenting the data in the same way. It's just a side point, and it just makes the point that the network is converging to a limiting behavior. Okay, so it turns out that particular limiting behavior can be captured by, again, this idea called the dynamical mean field theory, which leads to a bunch of summary statistics. So I'm not going to give the mean field theory as this a whole set of long equations, but I'll give you summary statistics. The summary statistics are basically two objects. One is this representational, what I'll call representational similarity matrices. These are the objects that we routinely actually study in neuroscience and present data in this way. So by some luck, or I don't know, a coincidence or something, they turn out to be also a sufficient statistic in this theory. I mean, there's a bunch of other variables here, but just to make sure what we're looking at is the same. So this phi here refers to a representational similarity at layer L, corresponding to two different inputs, mu and nu. T and S here correspond to different training times, so we need to actually calculate at different training times. Phi is a nonlinearity acting on a representational pre-activation vector at layer L of a data mu at time t, dotted into the same thing at time s for a different input, and divide by 1 over m because they're n-dimensional vectors. But that's just one set of summary statistics. There's other summary statistics. So you need to actually, this doesn't close on itself. And that's the gradient similarity matrices. So basically now these objects are, just technically what they are, is the derivative of the network's output with respect to a particular neuron's pre-activation. Now, if you know how the backpropagation algorithm works, there are some variables that you backpropagate. They're actually those guys. It's exactly what's been backpropagated to every neuron. That's what this object is. And then you have to construct another sort of object, like a matrix like this, using those variables as well. So those guys collectively are a summary statistic in the sense that they close, meaning that if I know them, I can calculate sort of them, all together. And then also, actually I'm not showing that aspect, but they're also predictive of performance in the sense that the following, if you knew these objects and you don't know anything about the weights or anything, you can directly calculate a network's output by just plugging in those objects in a differential equation and solving for them. And once you know a network's output, you know its performance as well. So in a sense, these are summary statistics from that point of view. Okay. And using them, you can calculate, this is just showing that I can calculate many things using them. For example, I can calculate loss curves for different values of future learning. I can calculate histograms of activations or pre-activations in a particular layer. That's what's being shown here. I collect all the neurons in a layer and make the histograms of the pre-activations. And then these two summary statistics basically capture all the statistics of this. Before and after learning, that's before, that's after, I believe, yes. And then also these kernels, I call them kernels in the slide, but similarity matrices in the previous slide, they're also captured by the theory itself, theory being the mean field theory and experimental measurements. So you can basically capture everything that you want to capture. Okay, good. So this was for backpropagation. Now, of course, I mean, there's a lot of criticism about backpropagation not being biologically plausible, and therefore, I mean, there are other learning rules people have considered that are sort of considered to be more biologically plausible, like feedback alignment, direct feedback alignment, or error-modulated Hebbian learning. So the idea in all of these things is basically the fact that in backpropagation, when you're like backpropagating errors, you have to multiply some variables with like the transpose of the feed-forward weight, which leads to the so-called weight transport problem. And that gets resolved by in these other kinds of updates by either replacing this by a random matrix or directly projecting the error through a random matrix or directly projecting the error itself and correlating with error modulating Hebbian learning. So you can again go and look for summary statistics in these kinds of architectures. And in these kinds of architectures, the summary statistic is basically, you still have the representational similarity matrix, but the gradient one is replaced by, so the true gradient dotted into a pseudo gradient being exactly what is being projected to a particular neuron from the error signal. So that's the idea over here. Okay. I mean, we've done many applications of this in deep learning, and so you can, if you want to follow that direction, you can take a look at these papers, including a recent collaboration with Cerebras Systems, basically testing some of these ideas in basically coming up with efficient ways of training deep transformers. But I want to go basically now discuss implications of what I presented for neural measurements. Okay, so first, I think this is an important point to make. Representational analysis is not sufficient, right? So even if we knew all of this, so this is the representational similarity matrix, the sufficient statistics that we looked at are saying it's not sufficient by itself to predict learning performance. You need to have access to gradient signals as well, gradient similarities as well. So that's an important point, I believe. I mean, like a lot of our efforts go into studying representations, but I mean, doesn't close basically. So another aspect of this is benign subsampling. What do I mean by this? Summary statistics usually depend on all neurons. I mean, here, the examples we see have that property. But, through our measurements, we only observe a subset. Is this a big problem? Now, because these are population averages, because basically, and in these particular theories, it turns out like these neurons are statistically exchangeable. Basically, we are very robust to subsampling. Which also means that reliable summary statistics can be obtained by recording a large enough subpopulation each day, but these doesn't have to be the same neurons every day, so that's a good news. And of course, there comes a question with this, what is the minimum number of neurons one must record? That's a great theory question, and Surya had some work about this from 2017, answering some of these questions. I won't go into this. Another implication of this is relates to representational drift. Because summary statistics are low-dimensional, meaning that they don't specify all aspects of a neural code. So there remains some invariances. Okay, for example, this particular thing would be rotationally invariant. I could multiply by a rotation matrix in right here, or I could basically permute neurons. So this basically is important also for observations about representational drift, right? So because these invariances can explain how neural codes can drift while behavior remains stable, right? Basically, if everything depends on this aggregate statistic, I can do whatever here to keep it fixed, and behavior must stay stable. In fact, many drift models exactly implicitly or explicitly posit changes that preserve these summary statistics, including work from my own lab, where this was showing that basically, we were trying to model a drift in place cell populations, and then this is place cells early in a learning episode and later, but in a way that preserves these representational similarity matrices. So in a sense, the whole representational quality of the population was preserved, but there was some underlying drift as well. Another aspect of this is universality. Universality is referring to certain coarse-grained statistics being asymptotically insensitive to the details of the distribution. And basically, there's a bunch of examples where I changed the underlying weight initializations from Gaussian to binary variables, for example, and basically, even though the underlying dynamics changes, the aggregate statistics are all the same, and therefore you get some universal behavior, which is also good news from the point of view of neural measurements. So to conclude, I've given you a bunch of examples of summary statistics in some well-studied and known cases, and a property of these models are that neurons are sort of statistically exchangeable, so that makes life easier and gives us all these nice properties. Now, of course, real brains impose additional structural constraints, right? There's a physical space that neurons live in. Spatial layout is important, topography is important, and so on and so forth. And we have all these diverse cell types. So, and just basically closing this with implications for future theory. And basically, if you want to take this path and then think about summary statistics as like a guiding principle for what to measure, right? So we need to take all these into account and develop summary statistics that capture learning dynamics under biological constraints. So with that, I want to acknowledge my students, especially Blake and Jacob, who helped me write this particular article, my funding, current and past, unfortunately, and then exactly, and this flash again, the particular paper here, and thanks, thank you.
Hey, thanks for Lena's talk. In the summary statistics, you needed to keep track of the entire data set, like a data matrix. Is there a way to algorithmically further summarize the data and not keep every single data point?
True. Okay. I said three things. So I could write down a version of this, which is mini-batch and so on and so forth. So you can track in each step a mini-batch version. Second, you could go after, so the first set of summary statistics that I talked about had this data averaging property. Now, from a machine learning theory point of view, that might be advantageous, but that also means that if you want to think about it from a brain point of view, maybe that means that you have to come up with a really good model of the data itself to be able to apply to this. But you're asking particularly about this DMFT, whether I can do this. And that's something we've been trying for a while. Couldn't figure it out yet, but I hope that we'll solve that. Yeah.
Great talk. And generally beautiful line of work, but to play the devil's advocate.
Please do, yeah.
It seems like a lot of the analysis relies on these mean field theory kinds of arguments. Mm-hmm. And when I've seen people try to actually fit mean field theory kind of results to neural data, the results have been kind of mixed. So to what extent is it worth being concerned about this?
I am concerned in the sense that, for the purpose of this particular talk, that these mean field theories were developed for artificial neural networks, and there we get good matches. And I'm trying to argue here that we should go after such things that is meaningful for brain data as well. And then I'm also saying that those things should satisfy these two desiderata. I'm very worried about this, and I'm posing that as a goal at this moment. Yeah. It's a question over back.
Hi, thanks for the talk. One thing I'm kind of wondering if you have any thoughts about is that going in to actually measure a gradient like you're describing in practice seems very difficult. For one, we may not know what the loss function is that the brain is using, and we may not even know in which manner such a gradient might be passed between neurons. Like it could be through neural activity, but it could also be through neuropeptides or some other form of communication. So I'm just wondering if you have any thoughts about that.
Yeah, I mean, for the particular example I showed, it's a gradient with respect to the last layer's activity. So you don't really need to know the loss function. So that's actually a perturbative thing. If you could perturb something and figure out how much things change at the end, and this is probably going to be all lost in noise anyway. So there may not be no hope there. It's true. But on the other hand, this is the reality. So what do we do with this? I don't know. Yeah. So if it is true that we have to measure this and then we can't, we have to do something about this. At least be aware of it. Yeah.
Thank you for the talk. One known problem of comparing learning trajectories between brains and networks is the choice of how you define a metric between what you compute as a gradient. So we're not sure what is the brain really, what are the parameters that are really optimizing, that the brain is really optimizing. Right. So how sensitive are these statistics to the choice of metric?
By metric, you mean?
I don't know, you're choosing Euclidean
you mean
space
you want to do Euclidean versus
all the weights have the same,
for example, natural gradient.
Yes.
Is that the idea? Okay, so I mean that doesn't change much. So all you need to do is introduce basically whatever that matrix that you want to multiply there is. I mean this is so that's not much of a problem. But so this is another example of such a thing. For example, the signals back are not exactly gradients, but some approximations to gradients. You can show that there exists again some statistics.
I see.
And then
we don't know what is
just not gradient, not gradient, but gradient dot pseudo gradient. Yeah. Right.
Okay. Thanks.
Thank you, Cengiz. With regard to what you said, so these sort of models, whether neuromass models or neurofield models, they were developed basically to get rid of the spatial information, and they make an average as a representative of the population. But in the last slide, you're saying, all right, this sort of method could be applicable to where we actually are measuring and we're trying to have all type of cell diversities. How do you reconcile these two aspects? Because then if you have to build a sort of like a neuromass model of each individual cell type, how do you explain this at a collective level to provide some statistics instead of
I mean, okay, so I mean, I guess implicit in the idea of a cell type is basically the fact maybe you can group them together. So meaning maybe there will be a certain representational similarity for a cell type A, cell type B, or something. I'm just making up at this moment. Yeah, but if you're telling me that it's not possible, that basically we have to track every neuron by itself and there is no summary statistics except for this, that's also a view. I don't think that is true though. Yeah.
No, that's not what I'm saying. But because you're mentioning that you can have a sort of like subsampling in your space. You say, all right, it doesn't matter if I track if this is a specific neuron, and I do agree with that. Because at the end, if you want to keep track of every single neuron, it doesn't tell you anything. But then if given, let's say, cortex, if you look at the cortex, there are like zillion type of cells, right? And if you want to build a sort of summary statistics for each group, then you have to actually extract away all the sort of like connection between these different groups together, right? So, so what does it resolve in that sort of approach that, someone say, hey, well, you know what, I'm going to map everything, connection, I'm going to measure everything, and then tell you what's happening, which is not realistic, but then, how do they...
Sure. I mean, let me make a point here. So I hear you. I didn't say that like summary statistics will also make it easier to measure because they're low dimensional. I mean, it might be that to be able to construct a summary statistic, you need to actually measure everything and somehow do some kind of averaging. I'm arguing that, in some cases, things are benign to subsample. There are some benign subsampling issues. So I'm just trying to argue that, like, what is it that you should be like calculating from your data that is basically capturing, sort of everything that you want to know about it in a functional point of view. That's what I'm trying to say. I mean, it can turn out that, like, to be able to even calculate the summary statistic, you do have to have, a large-scale measurements. That's also a fact, right? I mean, especially, for example, one of these things I showed is W.WK, right? So, I mean, that is a dot product of two vectors, high-dimensional vectors. The question is, like, how many of those dimensions you need to subsample to get, like, a good estimate of that dot product. Zach here.
So when you're trying to go from correlations, let's say, to connectivity, the causal relationships, that's hard. Ila Feed has a paper with Das showing that oftentimes you're screwed up with that. But in some sense, the right basis for understanding the computations is the connectivity, not the correlations. And in the same way that the mechanism of the plasticity is maybe likely at the synapse level, is it going to be possible, or is it hard, or is it within reach if we think of this distributed kind of computation to think of the gradients at the population level as giving you the information that you want that could eventually apply to the synaptic level where the mechanism is?
I guess is the question like the population level description of gradient, is that uniquely specifying what the synaptic level mechanism is? That
yeah, is it going to help us? Like if we had the plasticity rule, then we could learn. If
right.
we have the population level, can we do the same thing?
Right. I mean, okay, so by population level, I mean, here's a population level, right? So this G over here was a population level construct for basically learning related signals that you need to keep track of. Right? So, and I'm saying that like if I change the learning rule from gradient descent to direct feedback alignment, there's another G. Right? So there are different Gs for different learning rules, but once you have them, you can plug it into this equation and calculate what happens. So there is some kind of a coarse-grained signal here going from synaptic level learning to population level thing. That's an example of it. Okay.
Thank you for the talk. I was wondering if you've thought of any kind of structural constraints on this framework. For example, in brain, like nearby neurons end up encoding for similar stimuli, and especially with language where things might be happening in different parts of the brain. These kind of structural constraints might be important, and the summary statistics, if you use a structural network versus a random network, you'll get different kind of summaries.
I totally agree. We haven't done any work on this domain yet, but I totally agree that like that has to be taken into account. Yeah.
Thank you so much.
Thank you very much.